video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
Modern rotary drilling requires that a drilling fluid be circulated down the drill string and back to the surface through the annular space between drill pipe and hole. This fluid circulation is a critical part of the drilling process, and along with the hoisting, rotating, and control functions, is one of the primary elements of the drilling system. Circulation requires three things: a fluid, typically a liquid termed mud, a collection of cleaning and mixing devices to add or remove material from the system, and a high-pressure pump to drive the process. A well-designed and well-maintained drilling fluid is one of the most important factors in the safe, economical completion of any drilling operation.
In Unit 1 of this module, we shall review the functions of the circulation system and the composition and properties of the drilling fluid. Next, in Unit 2, we shall concentrate on the chemical makeup of drilling mud and the purpose of each individual fluid additive. The basic classification scheme for drilling muds will be defined. In Unit 3, we shall briefly describe the field testing procedures for determining mud properties. And finally, in Unit 4, we shall describe the equipment used to control the amount of solid particles in the mud system, an important factor in drilling optimization. But to begin, what are the functions that a drilling fluid performs?
Drilling fluids are used to perform the following 6 functions: to stabilize the wellbore while controlling subsurface pressure, to suspend drilled particles and transport them to the surface, to cool and lubricate the bit and drill string, to assist in formation evaluation while minimizing formation damage, to assist in supporting the suspended drill string, and to transmit hydraulic horsepower to the bit. Let's look at each of these functions individually. The normal fluid pressure gradient of the earth is about 0.465 psi per foot of depth, which is equivalent to a column of fluid weighing about 8.9 pounds per gallon. In many drilling areas, the weight of water plus accumulated drilling solids is sufficient to balance this gradient and thus prevent fluid flow into the wellbore from permeable formations. However, there are areas where abnormally high pressures require an increase in the density of the drilling fluid. In such cases, the drilling fluid will be weighted up with a high specific gravity additive. Typically, the column of drilling fluid exerts a slightly higher pressure than that within the drilled formations, a condition which results in some degree of fluid flow into permeable rocks. The drilling fluid must be designed to form a filter cake of solid particles against the wellbore wall, preventing significant fluid loss into the formation and thus stabilizing the hole. The addition of specially formulated natural clays to the drilling fluid normally provides this capability. These same clays also improve the drilling fluid's ability to transport the drilled rock cuttings to the surface, where they can be screened out and sampled for geological information. The fluid's viscosity permits it to carry these particles in suspension, and the clay increases the viscosity of the fluid. The clay also gives the fluid gel strength, a property which causes the mud to stiffen or gel when pumping stops, but allows it to liquefy again when pumping resumes. This property keeps the suspended cuttings from falling to the bottom of the hole when circulation is halted. With subsurface temperatures in the hundreds of degrees Fahrenheit and enormous pressures being applied at the drill bit's face, the need to cool the rotating surfaces of the bit's components becomes important. In addition, as a well is deepened, and particularly as it is deviated from vertical, the friction generated by the drill string on the wellbore walls increases. This friction adds to the wear of the pipe and increases the heat and torque on the drill string. The drilling fluid absorbs some of the heat and carries it to the surface, while the mud cake on the wellbore wall helps to lubricate the rotating pipe. The fourth function of the drilling fluid is to aid in the collection of geological information. The most obvious manner in which this is accomplished is by the transport of cuttings to the surface. By calculating the depth at which these cuttings were drilled, a lithological log of the hole can be developed. Coupled with detection of formation fluids in the returning mud, this information is the first glimpse of the subsurface available to the geologist. But the drilling fluid also provides important assistance to the logging of the drilled hole by permitting the shallow invasion of a known salinity filtrate into potentially productive formations. By minimizing the amount of this filtrate, the filter cake formed on the wellbore wall protects the formation from large amounts of foreign drilling fluids, which could damage the permeability characteristics of the formation. With average well depths increasing, the weight needed to be supported by the drilling rig becomes an increasingly important factor, particularly when running long strings of casing. The drilling fluid acts to buoy the casing as it is run into the hole, reducing the total weight that the surface equipment is required to support. Finally, the drilling fluid exiting the nozzles of the bit cleans the bottom of the hole and provides fresh rock for the bit's teeth. The amount of hydraulic horsepower available at the bit depends on how much energy is expended in moving the mud down the drill pipe. That, in turn, is dependent on the rheological or flow properties of the mud.
These 6 primary functions are several of the important reasons for using a drilling fluid. However, the fluid's ability to perform these functions is dependent on its composition, a composition considerably more complex than the name mud implies. Further complicating the situation is the fact that some components added to improve the mud's capability for one function may counteract the effects of components added to achieve another goal. When the variability of subsurface conditions is factored in, the maintenance of a quality mud can become a full-time job. Indeed, on some wells, a full-time mud engineer is required. But before we investigate the chemical makeup of a drilling mud, let us quickly review the circulating system itself.
The drilling mud travels through the circulating system as shown on this diagram. Mud is mixed at a mixing hopper from a base fluid, typically water, and the bulk materials stored on the location. From here, the mud goes to the suction pit, often a metal tank, where it is picked up by the mud pumps to begin its circuit. The pumps move the mud up the standpipe, through the rotary hose, and into the drill string via the swivel. It travels down the inside of the drill pipe and out through the bit nozzles into the drilled hole. There it picks up the drilled cuttings and begins its return journey up the annulus. Returning through the blowout preventers and mud return line, the mixture falls across the shale shaker, where the majority of the drilled particles are screened out and discarded. The mud then flows into the settling pit, then returns to the suction pit to begin the circuit again. While in the settling pit, the mud may be processed through various devices to remove finer sizes of drilled solids. The mud pumps which drive this system are driven by electricity or mechanical linkage powered by diesel engines. Generally, at least one auxiliary pump is provided for rate and pressure control in case of malfunction during critical periods, such as a kick. Mud pumps are positive displacement pumps which utilize a cylinder and piston arrangement. This arrangement may be duplex with 2 double-acting cylinders or triplex with 3 single-acting cylinders. Triplex pumps are lighter than comparably rated duplex pumps but operate at higher speeds. Pump output can be accurately determined by a volumetric calculation incorporating the cross-sectional area of the pump cylinder liner, the length of the piston stroke, and in the case of a double-acting pump, the cross-sectional area of the piston rod. By knowing the volume of fluid moved with each pump stroke and the number of strokes per minute, the engineer can determine the volumetric rate at which the mud is being circulated. Because worn liners and leaking valves decrease pump efficiency, regular pump tests at expected operating pressures are required to determine the percentage efficiency of the working pump.
We have been discussing drilling fluids as water-based liquids. In fact, the variety of drilling fluids extends far beyond this common example. Drilling fluids may be liquid or gas. Air drilling is used primarily in hard rock areas and in special cases to prevent formation damage or loss of liquids to underground fractures. Such drilling includes dry air drilling, where dry air or an inert gas is compressed and injected into the standpipe at a rate sufficient to clean the hole of cuttings, and mist drilling, where a foaming agent is used to help remove subsurface liquids from the hole. Occasionally, a mixture of air and mud may be used in aerated mud drilling. We shall concern ourselves with the more common liquid drilling fluids in this module, but even these come in several varieties.
Fundamentally, the drilling fluid is a two-phase system, with a continuous phase and a discontinuous phase. The continuous phase is typically water, but may also be oil. The discontinuous phase is normally made up of solid particles, but may also include droplets of oil in a continuous water phase or droplets of water in a continuous oil phase. Small amounts of gas may also be carried in solution in the liquid phase, either subsurface gases picked up from the drilled rock or air entrained at the surface. The solids in the drilling fluid are either part of the colloidal fraction or are inert. The colloidal fraction consists of the small reactive clay particles that hold part of the liquid phase within their structure and improve the viscosity and gel strength properties of the mud. Inert solids include weight-increasing additives as well as the drilled solids picked up from the drilling process.
We have already alluded to the most important properties of a drilling fluid, but we shall emphasize them here before we begin the unit on drilling fluid components and describe the chemicals used to control them. These properties can be grouped into three categories: density or mud weight, rheological or flow properties, and filtration properties.
Mud density is the weight per unit volume of the drilling fluid and is normally expressed in either pounds per gallon, specific gravity, or as a pressure gradient in psi per depth unit. The density of the drilling fluid must be controlled to provide sufficient hydrostatic head to prevent flow of formation fluids, but not so great as to cause damage to drilled formations or loss of whole mud into the formation. The pressure in psi exerted by a column of drilling fluid is equal to its weight in pounds per gallon times the depth of the column in feet times 0.052. So we see that a well bore full of 9.5 pounds per gallon mud exerts a pressure of 2,470 psi at a depth of 5,000 feet. In a normally pressurized area, a hydrostatic gradient of 0.465 would result in a formation pore pressure of 2,325 psi at the same depth. This is an overbalance of 145 psi, the pressure of which forces some of the drilling fluid's continuous phase into the formation and forms a filter cake on the wellbore wall. The most obvious flow property of a drilling mud is its viscosity. The physical appearance of a high viscosity mud may be described as thick, and that of a low viscosity mud is thin. The desired viscosity in a particular situation depends on the mud density, hole size, pump rate, drilling rate, pressure, and hole conditions. The apparent viscosity of a drilling fluid is a one-point measurement that is actually a function of three factors: the viscosity of the liquid phase, the size, shape, and number of solid particles in the liquid, and the forces existing among these particles. The base liquid viscosity is influenced by temperature, and oils are affected much more than water. Increasing temperature causes viscosity to decrease. The major viscosity building agents are the clays mentioned earlier, along with some organic polymers. Reductions in viscosity may be achieved by reducing solids, dilution, or by neutralization of the attractive forces between particles. The third major category of the mud properties is that of filtration behavior. The loss of liquid from a drilling fluid is controlled by the filter cake formed from the solid particles in the mud as they screen out on the drilled formation face. The liquid which passes through is termed filtrate. It is water in water-based muds and oil in oil-based muds. The term filtrate loss or fluid loss refers to this loss of liquid from the mud. In a well-designed mud system, a thin, tough filter cake will form, stabilizing the wellbore and protecting the formation. In this first unit, we have introduced the functions and basic composition of the circulation system. We have seen that there are 6 primary functions of a drilling fluid: controlling pressure, removing cuttings, cooling and lubricating, gathering information, providing buoyancy, and transmitting power. We have learned that the circulation system includes the drilling fluid, the mud pumps, and the mud cleaning equipment. Also, we have learned that the drilling fluid itself consists of 2 components: continuous and discontinuous phases. The continuous phases are most commonly water or oil. Finally, we learned that the density, flow properties, and filtration properties of a drilling mud are the most important characteristics in controlling its ability to perform its functions effectively.
In the next unit, we shall describe the individual components of drilling fluids and illustrate their functions. We shall also further subdivide the categories of water-based and oil-based muds. For now, please read section 1 in your manual and work the appropriate exercises. The first drilling fluid was created the day an ancient engineer dumped water into a bored hole to soften the rock and make it easier to bail out the cuttings. The use of drilling fluid to do more than that was not proposed until the late 1800s, when the search for petroleum prompted the addition of clay to help reduce the caving tendencies of deeper boreholes. Later it was discovered that heavier fluids could help control the higher pressures encountered at increasing depths, and high-density materials were added to the mixture. As wells have continued to be drilled to greater depths and into more hostile subsurface environments, new problems have been encountered, problems which have required more sophisticated additives. Some of these additives have, in turn, required other chemical agents to prevent them from adversely affecting the performance of previous additives. With several commercial suppliers of those chemicals serving today's industry, the total number of trade name drilling fluid additives now reaches into the hundreds. In this unit, we shall describe each of the primary functions of drilling fluid components and list the generic products used to perform these functions. Then, we shall describe a simple classification scheme for drilling fluids, which recognizes broad differences in composition.
The drilling fluid continuous phase, water or oil, may have components added to it to modify density, modify viscosity, control filtration, control flow properties, control pH, control loss of circulation, modify surface activity, lubrication, stabilize shales, inhibit corrosion, or inhibit bacterial growth. Let us look at each of these individually. Any substance denser than water itself may be added to increase fluid density. However, the ideal density modifier should be very dense, cheap, available in large quantities, inert and environmentally safe, easily ground into fine particles, and relatively non-abrasive. The substance which fits this description best is a mineral barium sulfate, commonly known as barite. It has a specific gravity of 4.5 and can be used to raise mud weights as high as 22 pounds per gallon. Other materials, notably iron compounds, have higher specific gravities, but are abrasive, have a tendency to settle out of the fluid, and have magnetic properties which can interfere with logging methods. The discovery of the benefits of clean, solids-free completion fluids has led to the development of high-density salt solutions for use during the perforation of a well's casing. Pure water weighs 8.33 pounds per gallon, while seawater, with a salt concentration of about 35,000 parts per million, weighs about 8.55 pounds per gallon. Clear solutions of chlorine and bromine salts of potassium, sodium, calcium, and zinc can be used to achieve weights from 10 to 20 pounds per gallon. Keeping the salts in solution at the various temperatures encountered is the primary challenge in the formulation of these products, and they are used primarily in the completion phase of the drilling operation. Viscosifiers are added to a drilling fluid to improve its ability to remove cuttings from the wellbore and to suspend cuttings and weight material when the mud is not circulating. Clays and natural or synthetic polymers are the materials most commonly used. The most common clay additive is bentonite, a fine-grained clay mixture which is mostly made up of Montmorillonite clay. Bentonite, also called gel, is added to freshwater-based muds to improve the mud's ability to remove cuttings and also to improve its filter cake forming capability. Clay minerals are crystalline in nature, having thin crystal platelets that stack together face to face. When mixed with water, these platelets separate as the clay hydrates or swells, increasing the viscosity of the mixture. Another clay mineral, attapulgite, is commonly used in saltwater-based drilling fluids. Attapulgite does not swell like bentonite, but must be dispersed by agitation. Section 5 in your manual has additional information on clay chemistry as it relates to drilling fluids. Another class of additive used to increase viscosity is polymers. These may be natural, organic compounds such as starches, gums, or cellulose derivatives, or they may be synthetic polymers derived from petrochemicals. These compounds are used for a variety of reasons besides viscosity control. The high molecular weight and highly branched high viscosity structure of the polymer compounds are what cause the increase in viscosity and gelation characteristics when they are added to a mud. Filtration control agents are compounds that reduce the amount of filtrate loss during and after the formation of a filter cake. This is achieved by causing the formation of a thinner, more compressed filter cake, either by deflocculating the clay particles, that is, causing them to separate, or by adding something which will plug the pore spaces in the filter cake. Bentonite is the material which creates the filter cake to begin with, of course, so it could be considered the primary filtrate control material. Starch is sometimes added to strengthen the filter cake, but breaks down with heat and agitation. Cellulose derivatives may also be used to reduce filtration in freshwater clay-based drilling fluids. Lignite, a carbonaceous coal-like material, is also used to reduce filtration rates in freshwater muds, particularly at higher temperatures, and several synthetic polymers have been designed to deflocculate clay platelets. Basic rheological control is achieved by controlling the concentration of the primary viscosifier, normally bentonite. However, occasions will arise when efficient control requires additives to independently thin the mud. These additives are variously termed thinners or deflocculants and cause a change in the physical and chemical interactions between clay solids and dissolved salts. Materials commonly used as thinners in water-based drilling fluids are plant tannins, such as the extract from the bark of the Argentine quebracho tree, lignite, mentioned earlier as an effective filtrate reducer, low molecular weight synthetic polymers, phosphatic chemicals such as sodium acid pyrophosphate or SAP, and lignosulfates, organic compounds which incorporate heavy metals. The control of many drilling fluid system properties is dependent on the relative acidity or pH of the fluid. The pH is an indication of the hydrogen ion concentration, ranging from 1, strong acidity, to 14, strong alkalinity, with a neutral solution at 7. The detection and removal of alkaline contaminants such as cement or gypsum rely on pH control. The pH also affects the solubility of many of the thinners mentioned earlier, as well as the dispersion and flocculation of bentonite clays. The most common materials for pH control are the alkaline hydroxides, most commonly caustic soda. When the mud weight exceeds the fracture gradient of a subsurface formation, or if a naturally fractured, highly permeable or vugular formation is encountered, the filter cake formation properties of the mud will not be sufficient to prevent the loss of whole mud to the formation. In this instance, lost circulation materials must be used to physically plug the voids and prevent a dangerous situation which might lead to the loss of well control. Such materials are categorized as fibrous, including paper pulp and wood or vegetable fibers, flake, including shredded cellophane and mica, or granular, such as ground nut hulls, calcium carbonate, or even used automobile tires. Once the material has successfully plugged the void, remaining material is removed from the mud system. Surface active agents, surfactants, are generally used to form emulsions of water and oil. Oil may be added to water-based fluids for several reasons, and surfactants act to stabilize the emulsion formed. Defoamers are surfactants used to reduce the foams formed by salt muds and when air or gas bubbles become entrained in the fluid. Lubrication to reduce torque and drag between the drill string and casing or hole may be accomplished by the addition of diesel oil, asphaltic compounds, natural or synthetic oils, gilsonite, or even glass beads to act as ball bearings. Shale stabilization materials tend to inhibit the hydration of water-sensitive clays encountered in subsurface formation. If allowed to hydrate, these clays can heave or slough into the borehole, sticking the pipe or causing unwanted viscosity problems. Depending on the nature of the shale, a variety of additives may be recommended, including polymers, potassium and calcium salts, and gilsonite. Oxygen is always present in the drilling fluid, and only a few parts per million is sufficient to cause corrosion. Chemical oxygen scavengers may be coupled with reduced entrainment procedures to reduce the problem. Microorganisms produce enzymes which attack organic additives such as starches. Biocidal compounds may be used to destroy these populations before they can cause problems.
These are just a sampling of the hundreds of chemical compounds used to control drilling fluid properties. Your manual has additional information on some of the less frequently used additives.
Despite all these additives, drilling fluid systems may be categorized as either water-base or oil-base, and the water-base category further subdivided according to the presence or absence of salts or chemical thinners. Water-based muds may be characterized as non-dispersed, non-inhibited, non-dispersed inhibited, dispersed non-inhibited, or dispersed inhibited. For example, non-dispersed non-inhibited fluids do not contain ions in the continuous phase which act to inhibit the swelling of formation clays, nor do they contain dispersants or thinners to control viscosity. Spud mud is typically such a fluid. It is designed to clean the hole and prevent sloughing of shallow formations with a mixture of water, caustic soda to adjust pH, and bentonite or attapulgite, depending on the salinity of the mix water. Polymer bentonite muds may be developed for use in low calcium formations. The polymers may be natural or synthetic, but the mix water may need to be pre-treated with bicarbonate of soda to precipitate any calcium. High calcium concentrations will cause precipitation of the polymers themselves. Non-dispersed inhibited systems are those in which salt ions are used to prevent formation clay swelling. Salt mud made with brine and attapulgite and supplemented with polymers or starch for filtration control is an example. Saturated salt muds are sometimes used when drilling through salt beds and are also made from attapulgite and polymers, but in water of extremely high salinity. Potassium chloride muds are also made with attapulgite or prehydrated bentonite and a 5 to 15% potassium chloride solution. This type of mud is effective in hard rock areas with reactive clay stringers. In dispersed systems, chemical thinners are added to maintain the clay platelets in a dispersed state. Lignite or lignosulfonate muds are very common for use at higher temperatures and where salt, anhydrite, or cement may be encountered. A typical lignosulfonate mud must be fresh water, caustic soda to a pH of 10 to 25 pounds per barrel bentonite, 5 to 10 pounds per barrel chrome lignosulfonate, and 1/4 to 2 pounds per barrel starch or polymer. Phosphate-treated muds are used to drill shallow wells with low mud weights and low temperatures. Again, calcium must be removed from the system to prevent precipitation. Dispersed inhibited systems are created by the addition of lime or gypsum. They derive their inhibitive properties from soluble calcium, and both require a chemical dispersant. These muds are used when drilling cement or anhydrite sections, which would drastically damage a non-inhibited mud. Oil-base or inverted emulsion systems are defined as those in which the continuous phase and filtrate is all oil. Water is only present as droplets suspended in the oil medium. The oil may be diesel or kerosene, mineral oils, or crude oil. The primary reasons for using oil-based drilling fluids are increased borehole stability, toleration of higher temperatures, and lower torque and drag. These factors become important in deep holes and directionally deviated well bores. Oil muds are generally insensitive to chemical contaminants which affect water-based fluids. While initial makeup cost is high, oil muds are generally less expensive to maintain than water-based muds and may be reused on future wells. However, they can be difficult to handle safely.
In this unit, we have discussed the components of drilling fluids. Primarily, they consist of bentonite or attapulgite clays for increasing viscosity, barite for increasing mud weight, natural or synthetic polymers for improving filtration and rheological properties, loss circulation materials for stopping mud loss, caustic soda to adjust pH, organic thinners to reduce viscosity, surfactants to create emulsions, and oils to provide lubrication. We have categorized muds according to their continuous phase as either water-based or oil-based, and we have further divided the water-based fluids according to the presence or absence of inhibiting ions or chemical thinners. It should be remembered in the midst of all this categorizing and generalization, however, that the wide variety of formations encountered in the subsurface and the combination of their components with the formulated drilling fluids make every drilling mud unique. Proper drilling fluid engineering requires that each well be treated as a special case. Part of doing that is the careful testing of the drilling fluid on a routine basis to monitor its characteristics as they change. These tests are the topic of our next unit. For now, please read sections 2 and 3 in your manual and work the appropriate exercises. As we have seen in the first 2 units, the efficiency of every drilling operation depends directly upon the properties of the drilling fluid. In this unit, we shall illustrate the common field tests used to evaluate the properties of the fluid during drilling. We shall be performing these tests in the laboratory for convenience, but remember that the equipment is designed for use under field conditions. These testing procedures are further described in your manual and in the API Recommended Practices 13B.
The most common mud tests are for mud density, apparent viscosity, rheological properties, filtration properties, and salinity. There are also variations on these basic tests, as well as more sophisticated tests for other properties, and they are detailed in your manual. The mud density test is conducted to determine the weight per unit volume of the drilling mud, and is performed using a simple mud balance. This balance consists of a base and graduated arm with cup, lid, knife edge, spirit level, and counterweight. The scales on the arm may include psi per 1,000 feet, pounds per gallon, pounds per cubic foot, or specific gravity. After collecting a sample of mud from the pit, the mud cup is filled to overflow. The lid is placed on the cup and rotated to seat firmly. Some mud will squeeze out of the vent hole in the lid center. With a finger over the vent hole, the balance is washed and wiped clean, and then placed with a knife edge on the fulcrum rest. The counterbalance is adjusted until the spirit level bubble is on the center line. With the balance steady, the mud weight may be read at the edge of the counterbalance nearest the fulcrum. After noting the reading, the balance is emptied, cleaned, and dried. This instrument may be calibrated by checking the density of clean fresh water. If in error, it may be adjusted by adding or removing lead shot at the end of the arm. The funnel viscosity of the mud is measured using a Marsh funnel and graduated cup. This apparent viscosity measurement is used to indicate relative changes in mud viscosity. The funnel is 6 inches in diameter at the top, 12 inches long, and tapered to a tube 2 inches long with an internal diameter of 3/16 inches. A 10-mesh screen is fitted across 1/2 of the funnel top to filter out foreign matter. The capacity of the funnel is 1,500 cubic centimeters. The mud is sampled from the flow line or pit using the graduated cup. The temperature is measured using a thermometer and noted. With the funnel held upright and with one finger over the bottom outlet, the mud is poured through the screen until the level reaches the underside of the screen. The empty cup is placed beneath the funnel and the bottom opening uncovered. The time required for the mud to reach the fill line on the graduated cup is noted. This line will indicate 1 quart or 1 liter, depending on the scale used. The funnel viscosity is reported as seconds per quart or as seconds per liter at the measured temperature.
The funnel viscosity is a relative measurement which can quickly give an engineer an indication of viscosity changes in the mud system. Actual viscosity is made up of 2 variables, plastic viscosity and yield point. These values, as well as a measurement of the mud's gel strength, are determined with a direct indicating viscometer, such as the rheometer, which is commonly found in most commercial mud kits.
The rheometer is a portable rotational viscometer, powered by the operator turning a crank which drives a spindle through a precision gear train. Speeds of 300 and 600 RPM are selected by a shift lever. Rotation for gel strength measurement is accomplished by a knurled knob. The test procedure is as follows. First, the test cup is filled to the scribed line with a mud sample, normally the same mud as was used for the funnel viscosity test. The temperature is recorded. The rheometer assembly is raised and the cup placed below the rotor sleeve. Then the assembly is lowered until the rotor sleeve is immersed exactly to the scribed line on the rotor sleeve. The leg lock nut is tightened and the speed shift lever is placed in the agitating position. The crank is turned clockwise for 15 seconds. Then the speed shift lever is moved to the 600 RPM position and the crank continually turned until a slippage is felt. With the dial reading steady, the 600 RPM reading is taken. Next, the lever is moved to the 300 RPM setting and the crank turned again until slippage is felt. While continuing to turn the crank, the second reading is taken at 300 RPM. Cranking is then stopped and the fluid left to rest for 10 seconds. With the speed lever still at the 300 RPM setting, the gel strength knob is slowly turned clockwise while the indicator dial is observed. The dial will peak and then break back. The peak reading is recorded as the 10-second gel strength. After letting the mud rest for an additional 10 minutes, the gel strength knob is again turned clockwise while the indicator dial is observed. This peak reading is the 10-minute gel strength. The plastic viscosity is the difference between the 600 RPM reading and the 300 RPM reading, and is recorded as centipoise at the measured temperature. The yield point is recorded as the difference between the plastic viscosity and the 300 RPM dial reading, and is recorded as pounds per 100 square feet. Initial gel strength is the 10-second peak reading, and is recorded as pounds per 100 square feet. The 10-minute gel strength is recorded in the same units. The filtration and filter cake building capabilities of the drilling fluid are determined by means of a standard filter press. This unit consists of a mud reservoir mounted in a frame, a filtering medium, a graduated cylinder for catching the filtrate, and a source of gas pressure. The test requires 100 psi for 30 minutes. It may be supplied from a high-pressure air system, from compressed gas cylinders, or from CO2 cartridges. The test is conducted at surface temperature with filtrate collected in the cylinder and the amount recorded as cubic centimeters per 30 minutes. The test is performed as follows. The filter cell is removed from the frame and disassembled. All parts are inspected to be clean and dry. The rubber gasket is placed evenly in the base cap and the filtrate tube is checked for freedom from obstructions. Next, the screen is placed in the base cap and dry filter paper placed on top of the screen. A second rubber gasket is placed on top of the paper, followed by the cell body. The body is turned clockwise until it securely fastens into the slots. The rubber gasket in the top cap is checked, and the cell is filled to within 1 inch of the top with a mud sample. The top cap is placed on the filter cell, and the cell body is secured into the frame. Next, the graduated cylinder is placed beneath the filtrate tube. A pressure of 100 psi is applied to the cell and the timer immediately started. The test is continued for 30 minutes. After this time, the amount of filtrate is recorded to the nearest 0.1 cubic centimeter. This filtrate is set aside for other tests and the gas pressure removed. The pressure is bled off the cell and the cell removed from the frame. The mud is carefully poured out and the bottom cap removed. This cap is then turned upside down on a solid surface and the filter paper removed. After a light rinse with water, the thickness and consistency of the filter cake can be recorded. The press is then carefully washed, dried, and reassembled for storage. Filter paper is not stored in the press. The amount of filtrate is reported, as is the filter cake thickness to the nearest 1/32 of an inch. Any physical description of the filter cake is also included, such as soft, firm, flexible, brittle, and so on. One of the most common tests performed on the filtrate is the chloride test, used for checking salt contamination and for determining concentrations in salt muds. This test is run on a portion of the filtrate and requires several pipettes, a silver nitrate solution, distilled water, a potassium chromate solution, a titration dish, and a stirring rod. The test is performed in the following manner. First, 1 milliliter of filtrate is pipetted into the titration dish and diluted to 40 to 50 milliliters with distilled water. To this is added 4 or 5 drops of potassium chromate solution. While continuously stirring, the silver nitrate solution is added drop by drop until the sample turns from yellow to a red color or to the first definite color change. A 0.1 silver nitrate solution is used if a low salt concentration is expected. A 0.01 solution is used if a concentration of 5,000 parts per million or more is expected. The number of milliliters of silver nitrate solution required to obtain the color change is multiplied by 10 when using the 0.1 solution and by 1,000 when using the 0.01 solution. The chlorides are reported as this value in milligrams per liter. If required, the chlorides may be reported in parts per million by dividing this value by the specific gravity of the filtrate. Parts per million sodium chloride may be obtained by multiplication of this value by 1.65. Following the test, all equipment should be thoroughly cleaned and dried. Other tests performed on drilling fluids include a high-pressure, high-temperature filtration test, a sand content analysis, an oil-water solids content determination, a methylene blue test for determining the cation exchange capacity of the clays in the system, a pH test, an alkalinity test, a test for carbonate and bicarbonate contamination, a lime content test, and a total hardness determination on the water in the mud. All of these tests are discussed in detail in your manual. Oil-based mud density, viscosity, plastic viscosity, yield point, and gel strength are measured in the same manner as for water-based fluids. Filtration properties are measured using the high-pressure, high-temperature filter press at downhole temperature and 500 psi differential pressure. The procedure for measuring salt content of oil-based muds is detailed in your manual.
The range of acceptable values for the properties measured in these tests will depend on the requirements of the mud system under actual drilling conditions. Here's an example of one mud program prepared for a wildcat well in Brazoria County, Texas. While it is certainly not a universal program, it does give a sense of the planning required.
The well is spudded with a bentonite and freshwater slurry having the following properties. Density, 8.5 to 9.0 pounds per gallon. Funnel viscosity, 40 to 60 seconds per quart. Plastic viscosity, 6 to 8 centipoise. Yield point, 20 to 30 pounds per 100 square feet. Gel strength, 6 to 10 for 10 seconds and 10 to 20 for 10 minutes. The viscosity is maintained with gel and water. Polyacrylate polymer may be added to prehydrated gel and pumped down the hole to sweep the hole of fill prior to running casing. This mud system is maintained for the first 1,700 feet of hole until surface casing is run. While the surface casing cement is setting, the mud pits are drained and filled with fresh water. Bentonite is added at 30 pounds per barrel, along with 1 sack of potassium hydroxide per 150 barrels. The breakover of the mud in the hole is begun while drilling out the casing shoe by adding additional potassium hydroxide while circulating. After the entire system has been circulated, lignite may be added to reduce filtration to below 6 cubic centimeters. Density is maintained at 8.8 to 12 pounds per gallon. Funnel viscosity at 36 to 45 seconds per quart. Plastic viscosity at 12 to 22 centipoise. Yield point at 4 to 8 pounds per 100 square feet. Gel strength at 0 to 8 and 4 to 10. And filtrate loss at 4 to 6 cubic centimeters. Alkalinity is maintained with the addition of lime or potassium hydroxide. Caustic soda is not used with this system. This mud is used to drill from 1,700 feet to 7,900 feet prior to running the intermediate casing string. The production interval from 7,900 to 11,800 feet is drilled with the same mud, but below 10,000 feet, high-temperature, high-pressure filtration control additives must be used. The properties are maintained as follows. Density at 13 to 17 pounds per gallon. Funnel viscosity at 40 to 55 seconds per quart. Plastic viscosity at 22 to 34 centipoise. Yield point at 4 to 8. Filtrate at 2 to 4 below 10,500 feet. And high-temperature, high-pressure filter loss at 16 to 20 cubic centimeters at 260 degrees Fahrenheit. Depending on the nature of the producing formation, a solids-free weighted brine may be circulated into the hole prior to perforating the casing to improve the chances for open high-capacity perforations.
In this unit, we have seen the basic field test procedures for measuring mud density, funnel viscosity, plastic viscosity and yield point, gel strength, filtration loss, and chlorides content. While there are many other important tests that might be performed, these 7 parameters are the values that most commonly appear on each morning report that comes in from every operating drilling rig. Other important tests that might be required depending on the specific situation are detailed in your manual. In the final unit of this module, we shall briefly discuss the equipment used to control the amount of solid material in the drilling mud. Solids control is an important part of an efficient and safe drilling operation. For now, please read section 4 of your manual and work the appropriate exercises. Only within the last decade or so has the importance of minimizing drilled solids in drilling fluids been fully realized. Minimizing drilled solids can save both time and money through increased drilling rates, increased bit life, and decreased mud pump maintenance. Some solids, such as weighting materials, are required in the mud system, but other undesirable solids may become incorporated into the mud during the drilling process, and their accumulation can cause increases in viscosity and mud weight beyond that required. The removal of solids can involve any or all of 4 treatment techniques: settling, dilution, mechanical separation, or chemical treatment.
Settling is accomplished by allowing the drilling fluid to remain in a near quiescent state for a time period long enough to permit the heavier particles to settle out. The success of this technique depends on the size and shape of the particles, their density relative to the fluid's density, and the overall retention time. Dilution is often used as a means of correcting mud property problems, but this method does not remove the solids, it only decreases their concentration. This technique is also expensive, since large-scale dilution leads to the need for storage of more mud or the discarding of usable mud as space limitations require. In many areas, the safe disposal of drilling mud is an expensive venture in itself. Mechanical separation devices are available in 2 basic types: vibrating screening devices and devices which utilize centrifugal force to separate the particles from the liquid. The common devices are a shale shaker, which can remove solids down to about 150 microns, a desander, which removes particles in the 50 to 70 micron range, a desilter, which operates like a desander for smaller particles, a mud cleaner, which combines a screen shaker and a desilter to remove solids down to about 75 microns while retaining barite particles in the mud, and a centrifuge, which can remove solids down to 2 to 5 microns if necessary. Let us look at each of these devices briefly. Various shale shakers are available from different companies. The double-decker shaker has 2 screens mounted on a flatbed frame. A common combination of screen mesh sizes is 30 mesh screen on the upper deck and 80 mesh on the bottom. Drilled solids down to 177 microns are removed by 80 mesh screens, as opposed to 840 micron particles on a 20 mesh screen. Desilters and desanders remove particles using a hydrocyclone. A centrifugal pump picks the mud up from the pit and spins it through the cone, separating the solids from the liquid mud. Since barite is ejected with the solids, desilters cannot be used in a weighted system. A mud cleaner is designed for weighted systems and consists of a desilter bank mounted over a small high-speed shaker. The overflow from the desilter is returned to the pit and the underflow is discharged over the shaker. A centrifuge is sometimes used in weighted mud systems to remove very fine particles. The mud enters a rotating chamber, and the centrifugal force separates the mud stream into 2 components, liquid phase and solid particle paste.
Chemical additives are sometimes used to flocculate the mud, causing aggregation of particles and facilitating their removal from the liquid. This approach is not recommended, however, due to the adverse effects of the additives on other mud properties. In this module, we have introduced the subject of drilling fluids and the circulation system. We have described the primary components of the system, and we have described the makeup of one of those components, the drilling mud itself. You have seen how the mud is tested to determine its properties, so that those properties can be monitored and adjusted through the use of the appropriate chemical additives. Finally, we've illustrated some of the equipment used to remove drilled solids from the drilling fluid. In other modules of the 200 series, you will learn about other facets of the drilling process. For now, please read the final section of your manual and work the remaining exercises. Good luck.
This program has been sponsored in part by the following companies: Agip, Aramco, Chevron Corporation, Mobil Oil Corporation, OxyCity Service Oil and Gas Corporation, Petro-Canada Incorporated, Phillips Petroleum Company, Schlumberger Limited, the Shell Companies, Texaco Incorporated.